Hello, curious minds. Welcome to the 8th episode of Facts of Universe with your own friend Alex. I hope you all are happy and healthy. Last week, we learned about the dark matter and dark energy. I hope you learned something new. I am sure that you shared with your circle too. Before starting with today's video, I want to ask you a question. Do you think our universe is moving? If yes, what is moving the universe? Where will it go, and how far will it extend to? Want to know the answers? Stick with me and hold yourself till the end of this video. The universe is an awe-inspiring expanse, stretching far beyond the limits of human perception. It is filled with billions of galaxies, each containing millions or even billions of stars, planets, and other celestial objects. These galaxies are not stationary, they are in constant motion, participating in a grand cosmic ballet orchestrated by the fundamental forces of nature. From the moment the universe began, with the explosive birth of the Big Bang, these galaxies have been moving, drifting apart as the fabric of space itself stretches and expands. This expansion of the universe is a well-documented phenomenon, first observed in the early 20th century by astronomer Edwin Hubble. Hubble discovered that galaxies are moving away from us, and the farther they are, the faster they seem to be receding. This observation led to the formulation of Hubble's law, which provided the first solid evidence for the expanding universe. The driving force behind this expansion is what we now call dark energy, a mysterious, invisible force that makes up about 70% of the universe and pushes galaxies apart at an accelerating rate. For decades, this understanding of the universe's expansion has been one of the cornerstones of modern cosmology. It tells us that, on a large scale, the universe is uniform and isotropic, meaning it looks the same in every direction. This is the basis for the cosmological principle, which assumes that the universe, when viewed on a sufficiently large scale, is the same everywhere, with no preferred directions or locations. But what if this principle is not entirely accurate? What if, hidden within the vastness of space, there are regions where the movement of galaxies does not conform to the expected patterns? This possibility became a reality in 2008, when a team of astronomers led by Alexander Kashlinsky made a startling discovery. They were analyzing data from the Wilkinson Microwave Anisotropy Probe, WMP, a satellite launched to study the cosmic microwave background, CMB, radiation, the faint afterglow of the Big Bang that fills the universe. The CMB is a crucial tool for cosmologists because it provides a snapshot of the universe when it was just 380,000 years old, a time when the first atoms were forming and light was finally able to travel freely through space. By studying the tiny fluctuations in the temperature of the CMB, scientists can learn about the early universe's conditions and the distribution of matter and energy throughout space. However, while analyzing this data, Kashlinsky and his team noticed something unexpected. They found that certain galaxy clusters were not just moving apart due to the expansion of the universe, they were also moving in a coherent direction, as if being pulled by some unseen force. This movement, dubbed dark flow, was unlike anything previously observed. It suggested that there was a vast region of the universe exerting a gravitational pull on these galaxies, drawing them toward it. The discovery of dark flow was both thrilling and perplexing. It challenged the conventional view of the universe as a uniformly expanding space. If the universe is indeed uniform and isotropic, there should be no large-scale flows like this. So, what could be causing this mysterious movement? And what does it tell us about the nature of the cosmos? As scientists began to delve deeper into the phenomenon, they realized that dark flow could be pointing to something far beyond our current understanding of the universe, perhaps even beyond the observable universe itself. The idea that there could be something outside the limits of what we can see, influencing the motion of galaxies, was both exciting and unsettling. It opened the door to a new realm of possibilities, where the universe we know is just a small part of a much larger, more complex reality. The discovery of dark flow set off a flurry of activity and debate within the scientific community. On one hand, the phenomenon was a tantalizing hint that there might be something out there, beyond the observable universe, influencing the motion of galaxies. On the other hand, it posed a direct challenge to the standard model of cosmology, which had been built on the assumption of a uniform and isotropic universe. To understand the significance of this discovery, it's important to grasp what the observable universe is and why it matters. The observable universe is the portion of the entire universe that we can see or detect, limited by the speed of light and the age of the universe. Since the universe is about 13.8 billion years old, and light from distant objects takes time to reach us, there is a horizon beyond which we cannot see. This horizon defines the observable universe, a bubble with a radius of about 46.5 billion light-years. Beyond this horizon lies the unobservable universe, a region that, by definition, we cannot access directly because light from those regions has not had enough time to reach us. However, just because we can't see it doesn't mean that the unobservable universe has no effect on us. If there are massive structures or other phenomena beyond this horizon, their gravitational influence could extend into the observable universe, potentially causing the kind of large-scale movement seen in dark flow. When Kashlinsky and his team published their findings, it sparked a wave of excitement, but also skepticism. The idea that there could be something beyond the observable universe affecting the motion of galaxies was revolutionary, but it was also difficult to prove. The scientific method requires evidence, and in this case, the evidence was based on an interpretation of the CMB data that was open to question. Some scientists suggested that the dark flow could be a statistical fluke, a result of random variations in the data, rather than a real physical phenomenon. The CMB is a complex data set with many potential sources of noise and error, and interpreting it correctly requires careful analysis. Critics of the dark flow hypothesis argued that the apparent movement of the galaxy clusters could be due to errors in the data or the methods used to analyze it. Others were more open to the idea, but cautioned that more evidence was needed before any firm conclusions could be drawn. They pointed out that while the concept of something beyond the observable universe influencing our own is intriguing, it is also speculative. Without direct evidence of what lies beyond the cosmic horizon, it's difficult to say for sure whether dark flow is real or just an artifact of our observations. Despite the controversy, the discovery of dark flow had a significant impact on cosmology. It forced scientists to consider the possibility that our universe might not be as uniform as previously thought, and that there could be large-scale structures or forces beyond our current understanding. This, in turn, led to a re-examination of the cosmological principle and the assumptions underlying the standard model of cosmology. The debate over dark flow also highlighted the limitations of our current observational capabilities. The universe is vast, and even with the most advanced telescopes and satellites, we can only observe a small portion of it. The discovery of dark flow underscored the need for new tools and technologies that could probe deeper into the cosmos, potentially revealing what lies beyond the observable universe. As the scientific community grappled with the implications of dark flow, researchers began to explore various theories that could explain the phenomenon. These theories ranged from the idea of massive structures beyond the cosmic horizon to more exotic possibilities like the existence of a multiverse or the remnants of a pre-Big Bang universe. Each of these theories offered a different perspective on what dark flow might be and what it could mean for our understanding of the universe. The mysterious nature of dark flow has given rise to a range of fascinating and sometimes speculative theories, each attempting to explain what could be causing this unexplained motion of galaxy clusters. While the phenomenon remains largely unexplained, these theories offer intriguing possibilities that push the boundaries of our understanding of the cosmos. One of the most straightforward explanations is that dark flow could be caused by massive structures beyond the observable universe. In this scenario, there might be enormous superclusters of galaxies, or even larger cosmic structures, exerting a gravitational pull on the galaxy clusters within the observable universe. These structures could be so vast that they lie beyond the reach of our current instruments, yet their gravitational influence extends far enough to cause the observed motion of the galaxies. This idea is grounded in our understanding of gravity and the large-scale structure of the universe. Just as the gravitational pull of a galaxy cluster can influence the motion of galaxies within it, so too could an even larger structure beyond the observable universe affect the motion of galaxy clusters within our view. If such structures exist, they would be among the largest objects in the universe, dwarfing anything we have ever observed. Another possibility is that dark flow is evidence of the multiverse, a theoretical concept suggesting that our universe is just one of many universes that exist simultaneously, each with its own physical laws and constants. In this framework, the observable universe is a bubble within a much larger multiverse, and the gravitational pull from other bubble universes could be causing the dark flow. The multiverse theory is highly speculative, but it has gained traction in recent years due to its potential to explain certain aspects of cosmology that are difficult to reconcile with the standard model. If the multiverse is real, it would mean that our universe is not unique, but rather one of countless other universes, each with its own history and characteristics. The idea that the multiverse could be influencing our universe is both mind-boggling and exciting, as it opens up a whole new realm of possibilities for understanding the cosmos. Yet another theory posits that dark flow might be a remnant from a pre-Big Bang universe, a scar left on the fabric of space-time by events that occurred before our universe began. According to this idea, the universe undergoes an eternal cycle of expansion, contraction, and rebirth, with each cycle leaving behind traces that influence the next. In this view, the dark flow could be the result of gravitational forces from a previous universe that continue to affect our own. This theory draws on concepts from cyclic models of the universe, which suggests that the universe is not a one-time event, but rather part of an ongoing process. If true, it would imply that the universe has no true beginning or end, but is instead part of an infinite loop of cosmic evolution. The idea that our universe could be influenced by the remnants of a previous universe challenges our understanding of time and space, offering a radically different perspective on the nature of reality. Of course, these theories are speculative and difficult to prove. The observable universe is vast, but it is still only a small part of the entire cosmos, and our ability to study what lies beyond it is limited. The true nature of dark flow may remain a mystery for some time, but the quest to understand it is driving new research and exploration in cosmology. One of the most promising avenues for future research is the development of new observational tools and technologies. Advances in telescope design, satellite instrumentation, and data analysis techniques are allowing scientists to probe deeper into the universe than ever before. These tools could provide new insights into the nature of dark flow, helping to confirm or refute the various theories that have been proposed. In the meantime, the discovery of dark flow serves as a reminder of the vastness of the universe and the limits of our knowledge. It challenges us to think beyond the boundaries of what we can observe and to consider the possibility that there are forces and phenomena at work in the cosmos that we have yet to understand. As we continue to explore the universe, we may find that dark flow is just one of many mysteries waiting to be uncovered. As we stand at the precipice of cosmic discovery, the mystery of dark flow remains one of the most intriguing puzzles in modern astronomy. Despite years of study and debate, we are no closer to a definitive answer than we were when the phenomenon was first discovered. Yet, this uncertainty is precisely what makes the quest to understand dark flow so compelling. The search for an explanation has already led to significant advances in our understanding of the universe. It has forced scientists to question long-held assumptions about the uniformity of the cosmos and to consider the possibility that our universe might be more complex and varied than previously thought. This shift in perspective has opened up new avenues of research, leading to the exploration of ideas that were once considered fringe or speculative. One of the key challenges in studying dark flow is the sheer scale of the phenomenon. The galaxy clusters affected by dark flow are millions of light-years away, and the forces driving their motion could be located far beyond the observable universe. This makes direct observation and measurement incredibly difficult, if not impossible, with current technology. However, this challenge has also spurred innovation, as scientists develop new methods and tools to study the universe in unprecedented detail. In the coming years, new missions and observatories are expected to provide fresh insights into dark flow and other cosmic mysteries. The James Webb Space Telescope, for example, is designed to peer deeper into space than ever before, potentially revealing more about the large-scale structure of the universe and the forces at work within it. Similarly, upcoming missions to study the cosmic microwave background, such as the European Space Agency's Planck satellite, could offer more precise measurements that help to clarify the nature of dark flow. But technology alone may not be enough to solve the mystery. The search for dark flow's source also requires new theoretical frameworks that can accommodate the possibility of forces or structures beyond the observable universe. This is where the interplay between observation and theory becomes crucial. As new data is gathered, it will either support existing theories or force scientists to revise their models, leading to a deeper understanding of the cosmos. The implications of dark flow extend beyond the realm of science. They touch on some of the most profound questions about the nature of reality and our place in the universe. If dark flow is real, it suggests that the universe is connected in ways we have yet to comprehend, with influences that reach across vast distances and perhaps even beyond the limits of what we can observe. This idea resonates with the human desire to explore the unknown, to push the boundaries of knowledge, and to uncover the secrets of the cosmos. As we continue to investigate dark flow, we are reminded of the vastness and complexity of the universe. Our understanding of the cosmos is still in its infancy, and each new discovery brings with it more questions than answers. But it is precisely this sense of mystery and wonder that drives scientific inquiry. The search for dark flow is not just about solving a puzzle. It is about expanding our understanding of the universe and our place within it. In the end, the true nature of dark flow may remain elusive, but the journey to understand it will undoubtedly lead to new discoveries and insights that will shape the future of cosmology. Whether we find that dark flow is the result of massive structures beyond the observable universe, the influence of a multiverse, or the remnants of a previous cosmic cycle, the quest to solve this mystery will continue to push the boundaries of human knowledge. And so, as we gaze up at the night sky, we are reminded that the universe is a place of endless possibilities and infinite wonder. The mystery of dark flow is just one chapter in the ongoing story of our exploration of the cosmos, a story that is far from over. As we look to the future, we can only imagine what new discoveries await us and how they will reshape our understanding of the universe. Thank you for sticking with us till the end of the video. I am sure all your queries are covered now. Share this knowledge with your circle so they don't miss out. Really, our universe is vast and so mysterious. I will join you next week again with another fact about our universe that you are unknown about. If you want to know about something or give suggestions, then comment below. And of course, don't forget to subscribe your favorite channel. Take care. See you next week.